Are we hearing that? What's that? What are we hearing? Sound? Or Lauren? Oh yeah. I hear something there. Yeah. Hello.
Hello, David. Can you hear me?
Yes. Yes.
Yeah. Okay.
Yes, I can hear you. Can you guys hear me?
Yes, we can.
Okay.
All right. So it looks like you have the slides all ready to go, up and connected.
Hopefully.
Well, I can see them. They look nice. So.
So we're next one.
Yeah, we'll get this.
What's the weather like in your respective locations?
Well, we have about 75 degrees and sunny here, so it's a spring weather for us.
Nice.
Yeah. I don't know about you.
50 and rainy here.
I think Seattle's really warm too. My wife's there right now, so.
Oh, great.
Yeah. So you're the only one with the bad weather right now.
I'll take it. It's good for the plants around here.
Right. If you see, my dog is here. So if you see a dog walking around, she wanted to hear the talk. She's really interested in spectral graphs and that kind of thing. So
fantastic. I think this may be the first canine attendee I've had for this talk.
Yeah. She might ask a question yet, but I'll translate.
Where is it go? Mago? Yeah. Just suppose you get mine. I know, right?
Okay. Well, is everyone ready to go? I think it's about 5 o'clock. Well, I guess 4 o'clock in the Pacific time zone. And what are you? You must be 7 o'clock or 6 o'clock, right? In Purdue, 6 o'clock?
7 o'clock.
7 o'clock. Okay. So we're spanning the U.S. time zones here. The Central time, I guess, nothing there. All right, well, I think we have some people online who don't have their video on, but for those of us that do, we can see and say hello. So I'll get started. We should keep on schedule here. So thank you all for joining us for the Spring SIAM Pacific Northwest Section Seminar. My name is Grady Wright from Boise State University. I'm the treasurer of the SIAM Pacific Northwest Section. So it's my pleasure to introduce our speaker today, who is Professor David Gleich. So let me give a little intro about Professor Gleich. So Professor Gleich is the Jayoti and Aditya, I think I said that right, but I'm not sure, Aditya Mathur Associate Professor in Computer Science, and by courtesy, the Department of Mathematics at Purdue University. His research is on novel models and fast large-scale algorithms for data-driven scientific computing, including scientific data analysis, bioinformatics, and network analysis. He is committed to making software available based on this research and has written software packages such as MATLAB VGL with thousands of users worldwide. Professor Gleich received his PhD in 2009 from Stanford University in computational mathematics and engineering. Since then, he has received a number of awards for his research, including a SIAM Outstanding Publication Prize in 2018 for his SIAM Review article on PageRank, which is a must-read, I would say, a Sloan Research Fellowship in 2016, an NSF Career Award in 2018, and the John von Neumann Postdoctoral Fellowship at Sandia National Labs in 2009. His research is funded by many agencies, including NSF, the Department of Energy, DARPA, and NASA. So with that introduction, I welcome you, David, and I'll turn the time over to you. Thanks.
Thank you. Can everyone hear me okay? At least just a thumbs up from some of the people. All right, great. I'm gonna switch over to my full slides and move everything else out of the way so I can see. Hopefully I don't screw up anything here. All right, so I'm going to tell you this afternoon or this evening, depending on exactly where you are, a little bit about some of the work we've been doing on spectral graph clustering with motifs and higher order structures. And so if you can't bear having suspense in talks or anything like that, you can go ahead and check out the archive paper, which was published in Science in 2016. And then we actually have software to do this in Julia and also in C++, but I think the Julia one is by far and away the most readable. And for those of you who know Julia, you know that they've been iterating fast in their development. And so this isn't, I don't believe this works with the most recent version, but it's not very hard to adapt. So it should be pretty straightforward to update it. All right, now what's going on? Okay, there we go. So what I'm going to tell you about today is just a little vignette of what we've been doing recently with our research team on higher order and multi-way data analysis. And so the particular topic we're going to focus on is essentially higher order structures and networks. But the broader theme to this research is, in case you haven't heard, there's all this data that's being collected and no one, well, sorry, people do have ideas about what they want to do with it, but everyone's still looking for new things that we can do with these really, really rich and interesting data sets we're getting these days. And so a lot of our stuff has been to take advantage of higher order properties. And so this is, in a nutshell, things beyond matrices. So things like tensors, your data comes in as a nice multi-dimensional array. We have a whole bunch of tensor methods that generalize spectral clustering through some nonlinear stochastic processes. And we also have a lot of research that involves higher order sequence data, so where you use more history for things like Markov models than just the recent state. So I don't have time to tell you about all of this stuff. I wish I did, because it'd be a lot of fun, but then we'd be here for quite a while. So we're going to focus in on what I think is the best introduction to this, which is in terms of networks. Okay, so I'm going to disclose my history on my sleeve here. So I was trained as a numerical analyst at Stanford, and so I can't help but look at the world in terms of a matrix. And so I don't think I'm breaking any new ground here when I say that graphs and matrices have a long and intertwined history. That is, these relationships between graphs and matrices go back very far. So matrices and graphs can both be used to represent relationships amongst a group of objects. And the earliest known observation I'm aware of this is a paper from 1928, where they look at essentially a graph of interactions between preschool children, or at least in the nursery school. And so they have all sorts of different types of interactions: talking, interference, watching, imitation, cooperation. And they have participants not sequentially, or sorry, not consecutively, but A, D, E, F, G, H, whatever these things are. And then they record the number of times each of these different interactions occur. And so this is an instance of a graph of interactions that they were representing as a matrix. And then once we have a graph or a network, a lot of times what people are interested in doing is studying those relationships and trying to use those relationships to tell them something new about their data. And so there are lots of different methods under this in the spirit of network science. There's things like centrality, which is who is the most important node. There's things like reachability. Is there a path between these nodes? And then the one we're going to focus on most is clustering. Does my graph or does my network or do my connections break into reasonably independent pieces? Now, this is just really the tip of the iceberg. Again, I could go on for a long time about these. But the point is, you can actually phrase most of these questions here very naturally as matrix computations. So that is things involving linear systems and eigenvalues. And if you want a few different references on this, there's a nice SIAM review paper by Ernesto Estrada and Des Hyam that looks at how matrix functions play a key role in a lot of different centrality operations. There's a book edited by Kempner and Gilbert that looks at how you can use matrix computations over a semi-ring to implement a lot of nice reachability questions. And then you can do all sorts of different spectral network analysis, sort of the flavor that I'm going to talk about here. And I love this reference by Brandis and Erlbach. Okay, so I'm going to cut to the chase here, and we're going to essentially give you the high-level conclusion of this, and then we're going to spend the rest of the talk explaining where that conclusion comes from. But you don't actually have to understand the explanation to understand the change in the methodology. So the suggestion based on our work would be if you're given a graph and you're given some analysis task based on its matrix. So we've got a graph here. This is a fairly benign graph. It's got a reasonably sparse looking adjacency matrix here. If you can phrase your analysis in terms of the adjacency matrix, what I would suggest doing based on our work is using the following weighted matrix. So the matrix W, where you take A and square it, and then you take a Hadamard or element-wise product of A with itself. And then just take this matrix W and stick it into whatever analysis algorithm you have that's based on the adjacency matrix. Okay, so why do I suggest that? Well, so the matrix W, this weighted matrix, A squared Hadamard A, counts the number of triangles that use a particular edge. And so a triangle is an example of a type of higher order structure in a network. So our network comes in as just these simple pairwise relationships. Based on those pairwise relationships, we can then extract triangles, which are a type of higher order structure. Okay, and this matrix W then counts exactly the number of triangles that use that edge. And if you want a quick derivation of that, there's a well-known relationship that says A squared counts the number of paths of length 2 in a graph. So if I have A squared counting the number of paths of length 2, then A squared Hadamard A just counts the number of times those paths of length 2 are closed into a triangle. And that then gives you a per edge measure. So you get the value on the closed edge. So why is that useful? Well, that's what we're going to work out through the rest of the talk, essentially. So just to summarize this again, this matrix W is going to arise naturally out of a framework we're going to derive for motif and higher order clustering when you tell it that the thing that's important for partitioning your network uses triangles. Why do I think this can be used more generally? Well, if you have anything that looks like the type of real world data, real world network data I'm used to looking at, what we find is that there are far more triangles in these things than you would expect in a lot of other types of networks. And when we look at these networks in terms of properties of these triangle, these weighted adjacency matrices, the W's, we often find they have better properties in terms of how the algorithms will perform. So we'll see a few examples of this towards the end of the talk in terms of partitioning stochastic block models. This isn't going to be the end of the story. We still have lots of open questions on this. So this is essentially a nice set of leading experiments at the moment. The other really cool thing about this is it's really, really easy to implement in any of the types of numerical computing languages that we like to use, or at least I like to use. So MATLAB, Julia, and Python all have fairly compact expressions for this. And if you know a little bit more about how these operations work, you can actually improve the runtime of these things quite a bit. Okay, so let's spend the rest of the talk sort of explaining where this stuff comes up. So just to recap this point, networks are sets of nodes and edges, or graphs, that model real-world systems. And so I oftentimes get this question, what's the difference between a graph and a network? Well, I would say a graph is a mathematical object. A network is a representation of a physical system, so some type of actual real-world system. And so a network is a representation of that system as a graph. So there would be graphs that are networks, but usually when we talk about a network model, we mean a mathematical graph. We can go much richer down that space, and the network scientists love doing that, but for this talk, it suffices to just treat graphs. So there's been a lot of research on treating data as graphs, or treating complex systems as graphs. And what this has shown us is that networks for real world systems have modules, communities, or clusters. That is, when you take these networks and you look at them, and you look at the networks that really correspond to physical systems, or real world systems. They could be non-physical, like things on the internet. They really do break apart into nearly independent pieces, or if you like a statistical bend, pieces that are highly non-random. And so different people call these different things. Out of the engineers and the physicists, we get the term module. Out of the sociologists, we get the term communities, and more out of the mathematicians and scientific computing folks, we get the term clusters. And there's a wide variety of different techniques and technologies to compute modules, communities, and clusters. But the sort of unifying theme behind all of them is they traditionally have been exposed using node and edge-based clustering methods. So a common setting is a community or a module is going to have edges that look non-random with respect to some null model. That's what gives you modularity. Another perspective would be a set of nodes as a community if they have density that's way higher than you would expect in your network, or if there's some type of trade-off, that is, you see a dense or a reasonably cohesive group that has only a few edges leaving it. And so that's what gives you methods like cut and conductance that we're going to spend a lot of time looking at. Okay, so the other thing that has come out of our insights into network analysis is there is lots of evidence that higher order connectivity patterns drive complex systems. So to put that another way, it's not the nodes and edges that really seem to matter for how these things function. And so this dates back to really a key paper by Milo et al. That showed that a lot of that there existed subgraphs of these real world systems that occurred far more often than you would expect at random. So things like triangles in social networks are an instance of this that I mentioned before. But each of these different motifs, so this is what's called a bifan motif, occurs far more often than you would expect. So triangles, so this observation for general networks goes back to Milo, but in special cases, it goes back even further. So triangles in social networks go back to the early 1900s. And this is really just a mathematical encoding of the observation that a friend of my friend is likely to be my friend. That is, if I have two friends, because they both interact with me, it's likely that they'll get to know each other at some point. In other places, we get certain types of bidirected paths in brain networks, and then certain types of essentially what are called signed feed forward loops in genetic transcription networks. So what we're going to do is we're going to call any small subgraph a motif. So when I use a motif or a higher order pattern, what I mean is just one of these little patterns. And then what we would do is we'd find all the places that little pattern occurs in our big network. So think of counting all the triangles in a social network. Okay, so the interesting thing about both of these realizations is that nodes and edges may not be the sort of basis elements of these networks. That is, if these higher order patterns or these motifs really do occur all that often, maybe we should look for clustering structure in terms of these motifs instead of nodes and edges. And that's really the approach we take here. So just to give you a really simple instance of this, if I asked you to take the following directed graph and to find clusters of motifs, and I gave you a a fully connected triangle motif, I don't think anyone would be particularly surprised when I tell you the answer is all these three sort of dense groups here. This is how we drew this network and how we sort of constructed it. Now, here's the interesting thing. If I asked you instead to cluster this network based on this particular subgraph, there's only two instances of this. We only have the instance between this node here and these two adjacent nodes, and this node here and these two adjacent nodes. So when I ask you to cluster on that one, pretty much your only answer is going to be just the nodes involved in that motif. And so you're going to get a very different set of clusters. You say, well, why would I be interested in clustering this bit? Well, if this bit is what is really driving the function of your network, then you wouldn't be interested in these dense clusters out here. What you'd be, well, I should use the term dense carefully here. You shouldn't be interested in these regions out here. What you should be interested in is in this region in the middle. To give you this in another instance, if you talk to a neuroscientist, what they know a lot of times is that the brain clusters just based on the fact that adjacent neurons tend to have more connections with adjacent neurons. This is just essentially the property of being a physical network. That's not what they're interested in getting at. What they want are these sort of command and control buses, more like these intermediate nodes here. So how does the command and control structure organize itself? Okay, so this is what we work out in our science paper. So we're going to generalize spectral clustering in order to do this. And so this is going to involve a notion of motif conductance. And we're going to be able to get a particular type of bound out of this called a Cheeger bound. That's going to give us a relationship in terms of the optimal solution. Back to the starting point here, this matrix W is going to emerge out of our framework. So again, when I suggested using it, I'm suggesting using it because it shows up as the right thing here. And this theorem, or sorry, this theory is going to apply to a whole bunch of other problems as well that we're not going to have time to tell you about. So what are we going to see in the rest of the talk? We're going to briefly review how spectral clustering works. Then we're going to see how to adapt it to work with network motifs. And then we're going to see this on real world and model data. Okay, so there are quite a few different views on spectral clustering. And so I'm going to give you the one I like. And so spectral clustering in a nutshell is a technique to partition a graph. So here we have a graph and A is its adjacency matrix by looking at eigenvalues, not of the adjacency matrix itself, but of a matrix like the Laplacian, or what I've actually written here is a symmetrized normalized Laplacian. To be slightly more precise, what we actually want are generalized eigenvalues of the following form. And what we really want are these small ones. So why are these all the right things? Essentially, this can be derived as a continuous relaxation of the conductance measure that we'll look at in a bit. But this idea of using eigenvectors to partition matrices or sets of interacting things in the form we're going to use it dates back to Fiedler, but it really ties in with some earlier work by Simon Andor, Doe, and Courtois as well. Okay, and so now, sorry, I should explain a little bit about how this eigenvector here. So this is actually an eigenvector of this graph. And if you look at the eigenvector, it actually breaks up into two regions. So I've helpfully labeled this axis. So this is the node entry. And if you look at this graph here, there are really two distinct groups. And so I've broken those two groups up in terms of their entries. And you can see there are essentially two clusters of entries in the eigenvalues. And it's this group up here that corresponds with this set of vertices on the left here. So this is, in some sense, the inspiration for how we're going to use eigenvectors to partition networks. Okay, so all of the theory of spectral clustering and the way I'm going to use it can be derived by trying to use this notion of conductance and come up with algorithms to work with it. So what is this idea of conductance? Well, if you want to sort of grandfather yourself into a problem, you'd say something like this. This is one of the most important quality scores used to identify network modules, clusters, and communities. And there I'm citing Schaefer in 2007. This is used all over the place. It's used to bound mixing times in Markov chain theory. It's used to bound a lot of stuff in bioinformatics as far as how well algorithms do. It's used to partition data sets in vision. But just like what is this measure conductance? It's a surface area to volume ratio. So it's a cut to volume ratio in a graph. And so cut is the number of edges that are removed when we separate S from S bar. So if you think of conceptually taking a set of vertices S and just pulling them out of the graph, so we take this set of vertices and just pull it out of the graph, then we would cut, I believe it's 7 edges in this case. Yeah, it is 7. Okay, so volume of S, this is something that's a little, takes a little bit longer to wrap your head around. This is what people often define as the sum of the degrees of vertices in that set. So I take each vertex and add a degree. The way I like thinking of this in terms of a volume is it's the volume of data you need to store for the adjacency information contained in S. That is, I need to store one piece of information for every neighbor associated with each vertex in S. And so if I just sum up how much information I need to store S and all of its adjacency information, it's exactly the volume of S. It's the sum of degrees. Now the conductance is the ratio between the cut and the minimum of the volume and the volume of the complement set. And so this minimum here is really important. If you didn't have the minimum, then if you're interested in minimizing conductance, you would really just say, fine, find me a very large set that has a small cut. And so you could immediately see that we essentially partition this network just by cutting off this little vertex down here, or I forget if this one up here might be a slightly better one. But suffice it to say, we'd essentially partition the network into one vertex and the rest, because that would give us a small cut and a large volume, and you'd never do better than that. So it's really this minimum that makes this problem hard. And in fact, you can show that there's a parametric LP that will solve this without the minimum term. Another way of looking at this is I like my objective functions to be symmetric, and this says that the conductance of either S or S bar is really the same thing. So it doesn't matter which side of the cut I'm pulling off, I get the same conductance score. There's all sorts of relationships back to Markov chains and mixing times too, and so there are other interpretations of this as well. In terms of what are we trying to do with this, we want small conductance, and that means a nearly independent or a good set. So we're going to associate small conductance with module structure or community structure. So the other nice thing about spectral clustering is it's got a whole lot of theoretical guarantees. So although finding the best conductance set is NP hard, so while this is true, we've actually had a lot of empirical success recently just by using Gurobi to compute these of a lot of networks. So we don't have a concrete explanation for why that is, but just although this is NP hard, you can actually do it, and we have done it for graphs with thousands of nodes. So back to these guarantees though on approximations. So this dates back to Jeff Cheeger in the 70s and Alana Millman over here. So Cheeger realized that you could essentially get a bound on the best conductance in terms of a real valued quantity on the Laplacian of a manifold, and then Alana and Millman essentially realized the same thing, but where you actually have a graph structure instead. And so what they said is, fine, you've got the eigenvalues of your Laplacian operator, or the normalized one in this case. These range between 0 and 2. And if phi star is the set of smallest, or the conductance of the set of smallest conductance, then there is a relationship between phi star and lambda 2. So this is the first non-trivial eigenvalue of your graph. So we know that the smallest is always 0, and lambda 2 is oftentimes called the first non-trivial one. This assumes you're working with a connected graph. So in honor of Jeff Cheeger, this type of relationship is called a Cheeger inequality here. Okay, so that's all nice if you want to bound the conductance of your graph, or the set of minimum, the conductance of the set of minimum conductance. But what people usually actually want is a set that gives you something that has provably small conductance. And so Milena Mihail realized an algorithm to do this in 1989, and then that was popularized by Fan Chung Graham in her book. And Jen relies in a few ways too. So we can find a set S that achieves the Cheeger bound by computing the eigenvector associated with lambda 2, and I always use the ARPAC software to do this. Once we have that, we can sort the vertices by their values in the eigenvector, and this is going to give us a permutation. So sigma 1 here is the ID of the first vertex in that order. Sigma 2 is the ID of the second vertex in that order, and so on and so forth. You might say, does it matter if we sort increasing or decreasing? And no, it doesn't, because we're going to look at, well, you'll see why in a second. So then what we're going to do is we're going to look at all prefixes of that sorted list. So we're going to let SK be the set of vertices that is induced by the first K entries in this ordered list. And we're going to compute the conductance of SK for all K. And so what this does is it takes our ordered list and just splits it up in lots of, or in K-1 different places, and we compute the conductance of each of those sets. There is an efficient way of updating this, so this computation is not problematic. You can do it in order E, where E is the number of edges of your graph. And again, note that for every set S, the conductance of S and its complement is exactly the same. And so that's why it doesn't matter that if we sort by increasing or decreasing. What we're then going to do is just pick the minimum of all of these values. And what these two showed is that phi m, the minimum, is bounded above by 2 times the square root of sigma star, where this is the set of best conductance. Okay, so let's just visualize this set here. This is essentially we're indexing SI here. So this is indexing SI for this graph, and these are our conductance values, and this is our eigenvector over here. And so if I sort these things from largest to smallest, so I sort them so that the vertex associated with, I think this idea is the first one, so this would be the first one, that would be the second one, so on and so forth. Then what I'm going to get here is, say, S of 5 is, or S of 4 here is going to induce a set on our graph. And then we're going to go in and compute the conductance of that set. And then we're going to grow our set by a few more vertices here. And we're going to compute another conductance. And then eventually for this graph, you remember how these two separate into pieces. What we're going to do is we're going to find the split between them, and we're going to evaluate the conductance of that, and we're going to find that it gives us a value of about 0.1. Okay, so that's spectral clustering, as I like to explain it. So this is theoretically justified only for undirected graphs. So you can't use this theory straightforwardly for directed graphs. There are various extensions to multiple clusters, so there's a lot of different ways, including some really nice theory on this. Weighted graphs are okay, so as long as you have non-negative weights associated with your edges, everything goes through quite nicely, and you don't have to compute your eigenvectors tremendously accurately. Essentially, you get a bound in terms of the Rayleigh quotient of whatever vector that you want to work with. But the problem is that current networks, current complex system models are far more richly annotated than just a simple undirected graph. So they might be directed, signed, colored, layered, multiplex, etc. And so just as an instance of some sign directed networks, we have a transcription regulatory network where X causes Y to be expressed and Z represses the expression of Y. So both of these target the same thing, but they have very different types of interactions. Also, in terms of food webs, if you partition them as if X eating Y is the same as Y is eating X, you're going to potentially be throwing away a lot of information in your data. So that's not to say that dropping the edges is necessary, or sorry, dropping the direction or dropping some of this information isn't the right thing to do. It's just, it's not clear how to extend spectral clustering to handle it. There was a lot of work on different strategies here, but our work, I think, gives a really simple formula to follow. And so the idea is what we're going to do is we're going to dispense with all of that rich structure and just say, hey, if you want to measure that rich structure, tell us a motif that does that. And so we'll give a whole bunch of examples with essentially a directed motif, but you could also just think of a motif as giving you a triangle. So in order to generalize these ideas to motifs, what we're going to need are notions of cut and volume that will work for a general motif. So just as a refresher from a few minutes ago, the cut of a set S is the number of edges that are cut when you sort of pull S out of the graph. The volume of S is the sum of the degrees. Now, it turns out this is not going to have a nice generalization the way we want. And so what we're going to write again is we're going to write volume of S as the number of edge endpoints in S. So think of it like this. For every edge in our graph, we're going to put a dot on the two vertices involved in that edge. And then the volume of S is just going to be the sum of the dots on vertices in our set S. Why do I like this? Well, it dispenses with this idea of degree and gives us a really straightforward extension to motifs. So what is the cut of a motif? So let's say we're counting the cut of a set S, which is the number of motif structures cut by S. Well, all we're going to do is just cut them, essentially take this idea of take S and pulling it out of the graph and see how many motifs we would need to cut or separate in order to do that. So essentially, this is just counting the number of motifs that don't have all of their vertices on one side of the cut. And then this notion of volume now extends quite naturally. So for each node involved in that motif, we put a little dot on the three endpoints here. So this is a triangle, so we'd have 3. And what we're going to do is we're just going to count up those dots. And then the motif conductance is exactly the same thing. So let's just see a quick little example of this. And if you guys are watching this on a projector, I hope the next transition works. Sometimes it doesn't, but if we take this graph and we have this motif here, so we've got a bidirectional edge that both links up to a single node, then the instances of that motif hopefully just shaded in on your screen. So you should see that it's now darker between 0, 1, and 4. And so let me do that again. So hopefully that, again, just shaded in on your screen. But the instances of this one are 0, 1, and 4, 0, 1, and 2, 0, 1, and 3, 5, 6, and 1, 7, 8, and 5, 7, 8, and 11, and there's one down here, 6, 9, 10. So those are all the instances of this motif in the network. And so the idea with this is we're going to throw away all the edges, and we're just going to look at these sort of sets of this. So you can think of this as actually inducing a hypergraph based on this motif. And so if you want to think of this as hypergraph partitioning, I completely agree with you. And there's all sorts of neat relationships with that perspective. So let's actually compute the motif conductance of this set S. And so the motif conductance of this set is going to be the number of motifs that we cut. And so when we take off this set S, we're only going to cut away this one motif, this 1, 5, 6. So the number of motifs cut is 1. Now, what's the motif volume? You might be tempted to say, hey, the motif volume should be there's one motif here, one motif here, one motif here, and one motif here. So my motif volume should be 4, except that the way we've defined this is that we want a single dot placed at every node inside these motifs. So this motif would contribute 3, this one contributes 3, this one contributes 3, and then this one only contributes 1. So 3 plus 3 plus 3 plus 1, I believe is 10. So that gives us a motif conductance of 1 over 10. So the key insight behind our entire idea here is that there is a symmetric matrix that serves as the appropriate tool to study motif conductance. So that is, if you are interested in motif conductance, you can take your directed graph A here, you take your motif, and you can build a nice weighted symmetric matrix WM over here. So this is this matrix W that I used at the start of the talk when the motif was a triangle. But the entries of this motif counts the co-occurrence of the motif pattern on an edge. And so you can see here that, remember, edge 7, 8 here was involved in 2 different motifs. And so that edge gets weight 2. The edge 0, 1 was involved in 3 motifs. So that edge gets weight 3. And every other edge in our network here just has weight 1. But we've removed things. So there was a directed edge between 7 and 3 in our original network. Here, we've dropped that edge completely because it doesn't participate in any of those motifs. All right, so the key theorem in words is that if you just do spectral clustering, so the spectral clustering that I explained at the start on WM, that actually yields results on this new notion of motif conductance. So that is, you don't have to do anything fancy and complicated in order to do spectral clustering out of motifs. What you have to do is you have to build this matrix and then run spectral clustering on it. So again, this counts the co-occurrences of motif pattern between I and J, and that's exactly what that matrix W did when the motif was a triangle. And so what this is saying, and this is what I'll explain in a second, is that essentially there's a one-to-one map between the objective functions of motif conductance and weighted conductance on this symmetric undirected graph associated with the matrix WM here. So here's just a really quick illustration of how this works. So remember, we had this example here where if I separate off the set S, I get a motif conductance of 1 over 10. If I just look at the weighted conductance in this weighted graph, well, what am I going to do? I'm going to get a cut of 2. And now the generalization of volume to a weighted graph is the sum of the weighted degrees. And so for node 0, I'm going to get 3, essentially, or my weighted degree will be 1, 2, I'm going to add 3 here, and then another 1 here. So that's 1, 2, 3 plus 3, and that's what I get with 6 down here. If you look up the weighted degree associated with node 1, I'm going to get 8, and then the weighted degrees associated with node 3 and 4 are both 2 because they only involve in 2 things. But although I cut 2 edges here, the volume term ends up scaling up by a factor of the motif size. And so this sum is actually 20. And so 2 over 20 is, we're back to our familiar ratio, 1 over 10. And so when we, so in case you're wondering how we got to this, essentially what we did was we wrote down the objective function associated with motif conductance, and we realized that the expressions involved could all be encoded in this matrix here. So when we drove this, or when we got it, essentially we started here and then realized you could explain everything in terms of this matrix here. So the reverse explanation, depending on if you like things to go forward or backwards, makes either more or less sense depending on your perspective there. But this suggests a really nice clustering algorithm. So we're going to form our weighted graph W of M. We're going to compute the Fiedler vector associated with lambda 2 of this motif normalized Laplacian. So we're just calling the normalized Laplacian of this the motif normalized Laplacian. And here's sort of how you would work that out. So again, we get the eigenvector of the symmetrized Laplacian here, and then we scale it by the inverse of the degrees. But remember, these are the weighted degrees now. And then we just run a sweep cut on F, where we use the weighted conductance measure. And so just as an example of how that works, so we've got essentially the order induced by our eigenvector here. So this is the permutation of vertices that we get from the Fiedler vector. So this vertex comes first, then we get vertex 3, then 4, then 0 and 1. And so you can see at some point, we pick off this set as the set of best conductance. We add in a few more, so we end up adding in this little region here, and we pick up another set that's pretty good conductance. It's not quite as good as our original set, and then as we explore the other ones, it just gets worse and worse. So I realized at this point that there's a slide missing that sort of explains a couple of these different ideas as far as a slightly more formal theorem, but let me just put that theorem into words here. So The theorem is just saying that essentially, if you do that spectral clustering algorithm I mentioned, then you get exactly the same type of Cheeger bound, but on the best set of motif conductance. The only caveat is that we need to put a restriction on the motif size for that theorem to be true. So that theorem is only true for motifs of size 3. And I'll return to this point at the end of the talk. Essentially, what goes wrong with motifs of size 4 is it's still true, but it's true for a slightly biased notion of motif conductance that penalizes equal splits of your motif. So you could think of if you've got a group of 4 nodes, now there is essentially 2 different ways of splitting them, 1 and 3 and 2 and 2. And what happens is the biased form you're going to get out of this motif weighted adjacency matrix is going to more heavily penalize even splits of this. Although I claim this is actually what you would want in a lot of applications. Okay, so with the remaining time, I'm going to talk a little bit about how we can use these to study real world data and a few cute examples here. So food webs are a really interesting type of directed network. So they model energy exchange. So I goes to J means that I energy goes to J. Another way of thinking about this is this actually means J eats I. So we take who eats who, and then we reverse all the links to get the energy exchange network. And now what happened with this network is we started looking at it, and we didn't know which motif was important. Thankfully, there aren't actually all that many directed 3-node motifs, and so we just tried them all. And we got the following picture. So this is the sweep cut profile. So this is essentially how well, how good of a motif conductance we can find as we vary the motif. And what we found was that there was this one particular motif, M6, where this profile showed substantially smaller conductance than anything else we looked at, including just edges, where you just drop direction. And so via the Cheeger inequality, we know that the conductance associated with this particular motif is actually better than any conductance you can get based on edges or even a variety of other motifs as well. And so this motif ends up being ecologically important in a way I'll explain in a second. Again, as Grady mentioned in my intro, I'm a big believer in reproducibility. So in case you want to actually reproduce that figure, we have this all on our Julia repository. And so this just ends up being a few lines of Julia code after you form W0 and W4. And we have a little demo that just walks through this. I think you might have to make a few little changes to get it to work on the more recent versions of Julia, though. So if anyone runs into trouble doing that, please just shoot us a note and we'll help you out. Okay, so what happens when we get this particular type of motif? We actually partition this network recursively into 4 very meaningful components. So these are what are called aquatic layers. So aquatic layers are what ecologists refer to as ecosystems near the shore. So there are essentially the benthic fishes. These are the things that live in the deep sea. There's the pelagic fishes and their benthic prey. So pelagic fishes live nearby the surface of the ocean. And then there's the benthic macroinvertebrates and sort of things that live along the sea shoreline. So there's the fish that swim in the deep sea, and then there's all the stuff that lives sort of along the coast. And you can see a lot of crabs and sort of macroinvertebrates over here. These are just all sort of micronutrient sources. So things like little bacteria and tiny things, so water flagellates. If we actually take the true aquatic layer associated with each species, we get a much higher accuracy using our motif than anything we could get with an edge-based method. And it turns out that this motif is actually known in ecology as a competition motif. And so what this means is that there are 2 species here that compete with each other and for the same source of prey. And so this is, we didn't know this when we started. After we started talking to a few people, they pointed this out to us, and then we were able to find a few references to this type of insight in the past. But we got this just purely based on data and looking at these conductance things. All right, so I'm very glad that you guys did not invite me to fly out there, because then I didn't have to experience the hub structure and the transportation air network. So this is a picture of what the air network looks like amongst the 50 biggest cities, and these are temporal reachability. So this is actually an unweighted graph, but it is directed because there are places you can reach within 7 hours going this way, but not coming this way because of jet streams and currents and flight schedules and all sorts of other weird things. All right, and so what we wanted to do is try and elicit hub structure out of this network. And so we used a motif that a lot of people had conjectured would indicate hub structure. And so this is essentially just a motif that is going to count length to paths or length to walks in this directed network. After we do that, you can already see that just by looking at the weights of this network, so the thick dark lines, I've now drawn the weighted matrix as a graph here amongst the nodes. The thick dark lines are the heavily weighted routes, and you can see that those occur between what people would call big hub cities. So you see places like Chicago, San Francisco, Los Angeles, Dallas, Houston, Washington, D.C., New York, Boston. I'm hoping that's Seattle up there, and including some places up in Canada as well. So what happens when we use our techniques on this? Well, we essentially get what's called a motif embedding. So rather than looking at this in terms of clusters, what we're going to use are the eigenvectors to give us coordinates for every vertex in the graph. So we're going to use the eigenvector associated with lambda 2 to give us our x coordinate, and the eigenvector associated with lambda 3 to give us our y coordinate. We're going to do this both for the motif weights and for the original edge based spectral, where we essentially just drop direction on the edges. Now remember, we set out to find hub structure. And so if you look at our embedding using the motifs, what you find is that the primary spectral coordinate, that is this eigenvector associated with lambda 2, has a number of very important airports as extreme points of that eigenvector. So we get places like New York, Chicago, Dallas, San Francisco, Phoenix, et cetera, et cetera. Whereas if you look at where a lot of those places are in the edge-based embedding, they're sort of right in the middle of the world over there. The other interesting thing is, and we didn't expect this, but the secondary spectral coordinate also gave us some pretty fascinating information. So remember that this primary spectral coordinate is essentially now telling us how much of a hub you are, right? So the big hubs are at this end. That means stuff down here over on this side are non-hubs. So Salina, Morgantown, Atlantic City. But then when we look at our y coordinate here, our secondary spectral coordinate, we find that it breaks down into things on the East Coast, Midwest, and then things on the West Coast over here. So we actually get this East-West split as well. If you do the same thing with the edge-based spectral embedding, you get Atlanta is next to Salina, and there's no obvious hub structure that comes out of this one, or no easy way of detecting it. One other really cool thing about this is if you actually had done this for the third dimension, what you would have found is that the third dimension actually splits US from Canada. Okay, so I've just got a few minutes left, and I wanted to just show a few ways that these help out giving numerical advantages to partitioning stochastic block models. So model problems are useful because we can do a lot of things with them that we can't do. And so for clustering, the model problem is the stochastic block model, which essentially plants really dense graphs. So we plant graphs where edges or pairs of nodes link up with probability P, and then pairs of nodes not involved in groups link up with probability Q, and we always have P bigger than Q. So this is an instance of a symmetric stochastic block model where each group has size 200. So each of these groups are 200 nodes. There are 5 groups, and the probability of linking or of having an edge within your group is 0.3, and the probability between your groups is 0.13. All right, so now if you're interested in partitioning these things, you might just be interested in computing that eigenvector yourself. And what we found here is completely fascinating, because if you just look at using the power method to compute the eigenvector itself, under a few conditions to make this work. So this is the smallest eigenvectors. You have to shift the spectrum, and then you have to deflate by a known eigenvector. What you find is that using the motif-weighted adjacency matrix actually computes one of the clusters faster. So you can see that you get separation from this cluster from all of the others much faster using the motif weights compared with the adjacency weights. And there's some fascinating numerical analysis in here that we're still unwrapping. This is just the same picture with a much more in-depth analysis. So the nice thing about these model things is we know everything about them. So we know that there's a threshold here that basically says above this threshold, no algorithm can get perfect answers. And so you see that our method really respects that threshold. There's another threshold that says where no algorithm can get any type of useful answers at all. We don't detect that one, or we aren't quite as sensitive to that one. But what this is really showing us is how much accuracy we get in picking off a cluster in terms of number of matrix vector products. And using these motif weights, you can do it in basically 10 iterations of the power method. Whereas for some of these other ones out here with the power method on the original adjacency matrix, you need approximately 100. There's a lot of things we don't understand about how this happens, but essentially what we're taking advantage of is a much bigger gap deeper in the spectrum. And so if you want to look at these things in terms of eigenvectors, so these are the eigenvalue distributions that you get as you vary that parameter. So I guess what I didn't explain in this previous one is we're varying a parameter here that controls how difficult this problem is. So we're seeing difficulty on the y-axis, how much work we need to do on the x-axis for the original method on the adjacency matrix, and the method on our weighted matrix. And so the point here is that there's some really neat numerical analysis properties that are coming up here, and we don't have explanations for these. So in fact, we don't actually know a nice closed form explanation for the eigenvalue law you get for this matrix A squared Hadamard A. It's definitely not a Marchenko-Pasteur law, which it kind of looks like. We're still trying to characterize what that is. There's still some other stuff going on here, but in the interest of time, I'm just going to summarize a little bit of work that people have done on this idea since we wrote our paper. So there's another interpretation of all this stuff that's based on random walks, and that was by Sturkakis in 2017. There is a way of doing all this stuff locally, so you don't even have to build your graphs, that we presented at KDD. Some of the coolest stuff is where is by Pan Lee and Olgita Mel and Kovic, who showed essentially how you can take a hypergraph view on this problem, and how there's a particularly interesting class of what they call submodular hypergraphs that gives you much better bounds in terms of how the conductance of these motif-weighted adjacency matrices compares with the true motif conductance. We've got some work on how you can use some flow-based techniques in order to do similar things as well. So there's tons of ideas based on the hypergraph theory, and I'm so excited every time I get a paper on this stuff. I was going to give you a quick rundown of some other stuff our research team is working on, but I am out of time. And so I'm going to end here, and I hope you guys have some questions and have enjoyed this.
Yeah, so I guess whoever has any questions, maybe you can just chime in when they're ready, or that's our exact process that works here, or you can raise your hand or something. Yes, there's a question popped up here. Can you see that, David?
Grady,
Yes.
I think there was a question online. So.
Yeah, I know. Did you see that, David?
Oh, sorry. No, I did not. Let me see if I can find that on my screen.
There's a little chat window a little.
Yeah, where did that go? I saw it a while back.
Yeah, I can also read it for you if you like.
Oh, there. I think no. Oh, yeah. Can A be a weighted adjacency matrix? Yes. So you can start off with a weighted adjacency matrix, and that's a idea we've explored a lot. The thing we don't know for a weighted adjacency matrix is what are motifs that can use it, or rather, if you think about it this way. Suppose you wanted to look at this idea of a triangle, and now you have weights on your adjacency matrix. How would you create a weight based on that triangle? And it's not exactly clear what you would do. You could take the product of weights, you could take the sum of weights, and we just haven't found sort of compelling reasons to take one or the other. We have tried a lot of these ideas: product, sums, geometric means, you know, all the sort of standard things you might think of for aggregating a set of three numbers into one. We haven't found a compelling case where it really makes a difference. And so I'd be super excited to find such a case. One other idea along that space is you could actually sort of threshold your weights into different scenarios, and then you could have motifs that involve, say, 2 low weights and 1 high weight edge as one of the things that you're interested in partitioning. So yes, A can definitely be a weighted adjacency matrix. The verdict is out on how best to take advantage of that, or how to set up, or where problems would be, where that would be a really compelling thing to look at.
I have a question. This is Bala Krishnamurthy from WSU, Washington State University. So you had a lot of pointers about extensions to hypergraphs. I was curious if some or most of the results extend to simplicial complexes. Has that been looked at?
That is another great question. So Austin Benson has been doing a lot of work on extending some of these ideas to simplicial complexes, and I'd have to check some of his more recent papers to see exactly how far they've gotten on that. But yes, the the 2 things I'll say there is Pan Lee has a nice alternative perspective where you actually can get some of these partitioning quantities on hypergraphs directly. And I believe in one of Austin's recent papers, he got something similar for a simplicial complex. So I would point you that direction.
Thanks.
I have a question, if that's okay. Hi, that's Malgo, actually. So I have this obsession of thinking about networks where you would have multiple connections between nodes. So for example, think of a, I don't know, toll road versus a non-toll road or something like this. So how would you deal with that?
So that's another great instance where you can use these motifs to sort of encode that structure in a slightly different way. So imagine you really do want to maintain multiple edges between pairs of nodes. You could define motifs where you're counting. One of the things you're looking for in your motif are sort of these parallel road cases. And express things in terms of them. So you might look at paths that have a lot of parallel roads, and be interested in partitioning your graph in terms of those instances, as opposed to just having a lot of roads between them. So one of the downsides to this framework, in case you haven't gotten that yet, is that it does leave a little bit more to the applications engineer or the specialist to specify some of these motifs. For things like directed networks, there's not that many 3-node motifs, so you can just sort of check them all. But sort of figuring out ways of targeting motifs for larger networks, or actually finding large motifs, is still one of our key challenges with this. We really sort of depend on people to tell us what they're interested in partitioning their networks in terms of.
Okay, thank you. Thank you.
Yeah, I actually have two questions, but maybe the first one's easy. I didn't understand why you were using the second eigenvalue or the eigenvector corresponding to that for the work, and then you were using the third in the other work. So why those?
The simple reason for that is you can show that the eigenvector associated with lambda 1 is essentially it's just a weighted version of the degrees. So it doesn't contribute any partitioning information. The slightly more refined reason is if you actually start with conductance as the discrete version of conductance as an objective function and try and round it down to real values, what you end up doing is you end up insisting that you're orthogonal to this degree vector of all, like the degree weighted vector of all ones. And that as a byproduct gives you that it turns out magically that gives you the second eigenvector. So I don't know if you like magic in your objective functions or not. So if you do, then that explanation is good. If you don't, then there's a slightly more technical reason underlying it, but it looks like magic.
Okay. And then my second question was, I thought that the results about the stochastic block model, that was really interesting. But in the power method, of course, this motif version is much more expensive, right? I mean, you have to compute this W matrix. Maybe you skipped over the slide showing the nice algebra that works out, but is it like 3 matrix vector products per iteration it takes?
So here's a cool thing. Once you compute W, it's the same amount of, like the matrix vector products take the same work. And the reason that's the case is because you have that Hadamard product with your adjacency matrix. So the non-zero structure it actually can be cheaper to do a matrix vector product with the motif matrix than the original one. Although you're right, forming that matrix is a non-trivial amount of work to start with. In practice, what you'd actually be doing is you'd be solving a whole family of these things. And so I suspect that would amortize over the faster runtime and the sharper separation you get. So I would claim, and I should also be clear, it's not like it's that expensive. So we could give a more formal bound on it. And we have in our papers. It's just not all that indicative of real world performance. If you're interested in enumerating triangles, it's pretty easy to do on up to billions of nodes within minutes to seconds.
So you don't actually do the matrix product, you actually do some other algorithm that just enumerates the triangles, or?
We usually use some other algorithm to enumerate. Well, so for that instance, everything is small and it doesn't really matter. But if we want to, like in a couple of our papers, we scaled this up to the Twitter graph where, it's 1.5 billion edges or something like that. And for those, we don't use the A squared Hadamard A just because there's some intermediate computation you can avoid.
Okay, thanks. Any other questions? Okay, well, I guess let's thank David again for a very nice talk. Thank you for joining us, David, and staying late at work.
Thank you, guys.
Thank you. And I have a traditional thank you to say to Yinjin from UW and the entire Applied Math for hosting us. Thank you.
Yeah. Oh,
Thanks, David. Thanks, David. Bye bye.
Maybe one more question. Are you posting these slides online, or are they available? Or
yeah, I can post them.
Okay.
So yeah.
There's also a recording. I also recorded on YouTube.
Oh, okay.
Yeah.
Okay, that's fantastic. Thank you.
Okay.
Thank you.
All right. See you later.
Thank you. Bye bye. Bye bye, y'all. Thanks.
All right.